In this 10th lecture on Schrodinger equation in 1D, today we shall discuss few selected problems. First problem is that a particle in box, particle in 1D box extends from 0 to A. What is the probability of finding the particle, between this A by 4? That is, what is the probability that a particle is in a state n would be found in the region 0 to A by 4? The probability of finding the particle in a region when it is in a state x phi n, then it is phi n star. This is the probability of finding the particle between x and x plus dx when it is in a state n. So this is phi n star of x, phi n of x dx integrated from 0 to A by 4. For a particle in a box, the energy eigenvalues are this: phi n of x is equal to root 2 by A, the normalization factor, times sine of n pi x by A. So if we write this factor becomes 2 by A, then integration from A to 0 to A 4, and this is sine square n pi x by A dx. If we take these two, then this becomes 1 by A integration 1 minus cos of 2n pi x by A dx from 0 to A by 4. If we integrate this, the first term gives you A by 4, and for the second term you have to integrate it minus A by 2n pi, A by 2n pi, then sine of 2n pi x by A within limit 0 to A by 4. It is 0 in the lower limit, and in the upper limit we will have 2n pi by A into A by 4. So this is n pi by 2. So this is n pi by 2, and sine of n pi by 2 is this is and sine of n pi by 2 is equal to 0 when n is equal to 11 and is equal to minus 1 to the power n plus 1 when n is odd. That is, for 90 degree it is 1, for 273 degrees is minus 1, and so on and so forth. And so we get the result. If we are given any range between A, 0 and A, we can integrate it accordingly. Now coming to the second problem. Again, a particle in a box. Most of the problems are from there excepting two, because these are very easy to work out. We have a particle within a box, and we are to calculate the expectation values x when it is in a state this, x square when it is state in this, and then we are also to calculate x in classical mechanics as well as x square in classical mechanics. Let us first calculate this one. and we are to integrate from this 2 by a from normalization factor, and then x sine square n pi x by a dx from 0 to a. This can be written as 1 by a integration x 1 minus cos of 2n pi x by a dx, and integrated from limits this. The first part is 1 by a times x s square by 2, the first part, and second part is 1 by a integration x cos of 2n pi x by a dx from 0 to a. Let us calculate this one. We consider this is first function, this is second. This is 0 in both the lower and upper limits, because and the lower limit it is 0 because sine of x, and upper limit it is 2n pi sine of 2n pi, so it is 0. So we have minus a upon 2n pi, this factor, and when we integrate it again same factor, so this cos of, this is when x is equal to a cos of this is cos of 0, and cos of 2n pi is 1, so this is 1, so the result is 0. So we get, as this is equal to 0, we get it is a by 2 as the average position. So the well extends from 0 to a, and the average position of finding the particle is at its midpoint. Now come to the case of x n square. Then we will have similarly we can write it as 2 by a factor comes from normalization. This 2 is utilized over here, and the result is 1 minus cos of 2n pi x by a dx from 0 to a. Now so this result is 0, we know, and we need to calculate a similar integral. X square this part is 0. A by n pi, this factor, when we integrate it, another minus a by 2n pi, then we will have cos of 2n pi x by a this is equal to a square by 2n square pi square. Then this is 0 in the lower limit, and in the upper limit it is a cos of 2n pi, which is 1. And when we invert it, integrate it, the sine function will come, which is 0. And this is equal to 1. And on putting this value over here, we can calculate the calculate the x square average. Now we come to the corresponding calculation of x and x square in classical mechanics. Since the particle is moving back and forth between 0 to L, the probability of finding the particle in this case is 1 by a, so it is equally probable. So we write x in classical mechanics is probability is constant 1 by a x dx from 0 to a, so it is a by 2. And similarly x square cm is 1 by a 0 to a x square dx, this is a cube by 3 a square by 3. Now coming to the third problem. This third problem is, we have again a particle within a box of length a extending from 0 to a, and the particle is found in a state given by, the particle is found in a state given by psi of x0 is equal to some constant a, sine of 5 pi x by a, cos of 3 pi x by a, 3 pi x by a, and our task is to normalize it, to expand it in terms of energy eigenvalues, energy eigenfunctions, and to find out psi of xt, and then finally whether it is a bound state, whether it is a stationary state or not. So we start like this. This is a by 2. So there will be a 2 term comes. So this is sine of this plus this by 2. So a sine of this plus this, 5 and 2, I missed, it is 2. 7 pi x by a plus sine of 3 pi x by a. So this factor has to be adjusted. You see, this is normalized phi 7, this is normalized phi 3. So we write it as a by this. So if we want to normalize this, we have this is equal to 1. We will have a square by 2a. Then integration 0 to a phi 7 star phi 7 plus phi 3 star phi 3 plus phi 7 star phi 3 plus phi 3 star phi 7. On integration, this is equal to 0, this is equal to 0, this is equal to 1, and this is equal to 1, as the states are orthonormal. So we will have only 2. One from here, one from there. So a is equal to root 2a. So a by this factor should be 1 by root 2. I have made some mistakes somewhere. 2 by a. Okay. So if we write a square is equal to some mistake. Let me first find out. A very silly mistake has been done. This part should be 2 by a. This is root 2 by a. So the factor that has to be considered is a by root 2. So this factor will be a root a by 2 root 2. So when we normalize it, it will be a into a, and denominator it will have 8. So the part will be, this part will be a square a 8 into 2. So this is a square a by 4 is equal to 1. That gives you a is equal to 2 by root a. So that this factor a by root a by 2 root 2 is equal to 2 by root a for capital A, and then a 2 root 2. So this is 1 by root 2 as it should be. So this normalized to a function is now the next part is to calculate so we have answered two questions. One is it is the normalized wave function, and the wave function has been written in terms of the energy eigenfunctions. Then the problem is to find out what is the time evolution. Time evolution state, the time dependent state is psi of xt is obtained from this as 1 by root 2 times phi 7 of, we should write it, this can be written as here we have written phi of nxt is equal to phi n of x e to the power minus I ent by h cross, and en is equal to epsilon n square, where epsilon is h line square twice ms square. So this is written as 1 upon root 2 phi 7. You can write phi 7 explicitly, or you can write phi 7 e to the power minus I 49 7 square 49 epsilon t upon h cross plus phi 3 of x e to the power minus 9 in the third state, 9 epsilon t by h cross. This is the time evolution of the state. Now the question whether this is the stationary state. For stationary state we must have psi of xt is equal to e of h psi is equal to e psi. Let us check. When Hamiltonian operates on psi of xt, we will have 1 by root 2. Then Hamiltonian operates only in this, not in this. So we will have, when it operates on this, you will have 7 epsilon times here the condition that I have written, that h operating on phi n gives you epsilon n square phi n. Sorry, n square. Actually it gives you n phi n, then it is epsilon n square phi n. This is not equal to, this cannot be written as something into phi on of xt. The conclusion is that not a stationary state. We have argued in the on the discussion of Schrodinger equation that if we make a superposition of states, make a state which is a superposition of the state which are the solution of time independent Schrodinger equation, then it is a solution of this. So that's all. Then come to the second problem. Second problem is again a similar problem, a particle in a, so this is the fourth problem, is again a similar problem. The state of the system is given as psi of xt when is 1 by root 2, it is already normalized. Phi 1 of so we have a particle in 1D box, and the time dependent state is given by this. First, to find probability density, rho of xt is equal to one upon 2. Then if we write it explicitly, it is epsilon t upon h cross plus phi 2 e to the power minus I 4 epsilon t by h cross. Plus, because we are taking the complex conjugates. This is from psi star. If we multiply this is psi 1 star psi 1, then if we multiply this with this plus when we multiply this with this psi 1 star psi 2 e to the power this factor and when we multiply this by this we will have psi 2 star psi 1 e to the power plus I 3 epsilon t upon h cross. since psi 1 psi 2 are real for the present case, we write it as psi 1 square psi 2 square plus this part is written as twice psi 1 psi 2 cos of 3 epsilon t by h cross. The probability current density is time dependent, so it is a non-stationary state, as the probability current density has time dependent, so it's a non-stationary state. As rho depends on time. Now the next part is to calculate the time dependent position. So we are to calculate except t in this state. So the definition is psi star xt x psi of xt dx from 0 to a. For this part we write this is plus plus I 4 epsilon t by h cross times x dx. Earlier in a calculation we found that x in n is a by 2 in any state. So if we multiply this and 1 by 2, from this we will have a by 2, and from this we will have a by 2, and this part is yet to be evaluated. Then we are to calculate this integral, and this integral is integration phi 1 phi 2 x dx from 0 to a is equal to is equal to 2 by a integration x sine pi x by 2 sine of 2 pi x by a2 dx. This can be written in terms of 2 cos function. This is equal to 1 by a integration 0 to a x cos of difference of this, so pi x by a minus cos of 3 pi x by a dx, and when we integrate to completely, this result comes out to be minus 5a by pi. So this says, we see that it is a, so half a minus 5a by 2 pi cos of 3 epsilon t upon h cross. This is an oscillatory position. The particle position oscillates with time. Another very simple example we are considering, and this is the last example on particle within an infinite well we are going to consider, is that we have a particle in an infinite well of width a, and when the particle makes a jump from n is equal to 2 to n is equal to 1, what will be the frequency of the emitted radiation. Note that the each of the state that we are talking about is a stationary state, as they are obtained from the solution of time independent Schrodinger equation. So the energy level is n is equal to 1, n is equal to 2, E2 is 4 epsilon, and E1 is epsilon. So when an electron makes a jump from 2 to 1, delta E is equal to E2 minus E1 is equal to 3 epsilon, and this appears as h nu. So this will be the frequency. Another problem is that there are 3 electrons within the well. What is the minimum possible energy state? 3 electrons are there. The electrons being fermion, so there cannot be more than 2 electrons in a state. So this state is filled up by this, and another one will be in the third state. So the energy of 3 electron system is equal to 2 epsilon plus 4 epsilon is equal to 6 epsilon. 6 epsilon. This is the minimum possible energy.